Yeah, okay. So hey guys. Yeah, so like the talk is supposedly a talk about an introduction to Haskell. But yeah, I think we might want to start recording. Have you?
Yeah, I started recording.
Yeah, cool. Yeah, but I mean, I feel like introduction to Haskell is like a complicated thing to do, and yeah, like it sort of like really varies with the audience how you want to like talk about Haskell. Um, Yeah, so essentially what I'll be talking about is in some sense what I got out of learning Haskell, and like in a sense why I think folks should learn Haskell. So that's going to be the sort of focus of what I'll be talking about. Yeah, and feel free to like interrupt me if you have any questions. If not, I'll just keep going. Um, cool. So let's begin. Right. So like you know, yeah, so I guess like the first question is what is programming, right? And very often programming feels like building a cathedral. And the reason for that is that, first we build something and then we pray that it works, right? It's like most often, we don't really know whether the code we're writing actually works or not. And yeah, and testing code is difficult and programming is difficult. um, yeah, so perhaps you're not convinced that like writing code is hard. So therefore I'm going to go through a couple of examples, um, which essentially show off the things that make writing code hard, and how Haskell helps in yeah, and essentially how Haskell helps us avoid these kinds of pitfalls. um, yeah, so for example, we can consider this like really simple C program, well, C++, which defines a function f, and this function takes an integer called x, and it simply returns whether x plus 1 is greater than x. Yeah, and we have a main which tries to evaluate this. Now, naturally, the answer ought to be true or 1, because 0 plus 1 is 1, which is greater than 0. And yeah, and like if you write the code and execute it, you'll see 1. So yeah, and so like we might be tempted to think of this function as a function from naturals to booleans, which returns true if x plus 1 is greater than x and false otherwise, right? Like that's the definition of the function. Um, but this is like really silly because we know that x plus 1 is always greater than x. So like it doesn't make sense to define it this way. Rather, we can just convert the function to a function that always returns true. But like, is this really a sane thing to do? And that's the question. And it turns out that, well, not always. And the reason is that this plus operation that we have, it's not actually like addition of naturals or integers, right? It's doing modular arithmetic. So yeah, and so like if we try to call f with uint32 max, uint32 max plus 1 wraps around, that gives us a 0, and then we have 0 greater than uint32 max, which is untrue. Yeah, and the output of this program is going to be 0. So the real definition of this function is in fact something like this, where we're taking x and we're adding modulo 2 to the 32, right? um, where addition modulo 2 to the 32 is something that's more complicated, like you first add and then you take modulo whatever. Yeah, and so it's like even with such a naive and simple program that like does nothing, it's like our reasoning sort of screws us over, and like we need to be careful when we think about these things. So reasoning about programs is like somewhat complicated, because of the reality of the hardware on which they run in this case. Like ideally we would like to compute on like naturals or integers or whatever, but we can't. Yeah, so we do modular arithmetic and we pay for it. Um, so then like there's a second example, right? So like this is sort of an uncontroversial statement that yeah, that like if you have, then multiplying it by 2 is the same as adding it twice. And yeah, and in this case I can't even cheat you with like modular arithmetic trickery, because the same identity holds even if you're doing things in modular arithmetic. So that's not, yeah, so that's not going to be a catch. However, there is a catch. So for example, right, so like let's just consider a program that tries to return 2 times get car, right? So what does this program do? Well, yeah, uh, so like this program waits for you to type a character and then it returns 2 times the ASCII code of that particular character. Now, like I better not convert it to get character plus get character, right? Because yeah, because now this program expects you to give two inputs, and it then adds the ASCII values of both of these programs together. So this mathematical identity that we have, which says 2 times x equals x plus x, itself doesn't work. And okay, so like let's try to examine what's going wrong, right? Like, what is getchar? So getchar claims that it's a function that takes no inputs and returns an integer, right? But then, like, if you think about it mathematically, like, what does that mean? So yeah, so that means that it's a function from an empty set, and it ought to return an integer. But then, like, such a thing is impossible, right? Because like whenever you have a function should like return a function can only return a value when you call it with something. So like this definition definitely doesn't work. It can't ever return an output. So then maybe you decide to like change the definition a little bit, and you say like, okay, like there is some implicit input that's going, which I call star. But now, like, if you have such a function, because in math, like, a function is deterministic, right? Like, you can't have a function that does different things when you call it different times, like, because yeah, that's what a function is. So like such a function can only pick out a given number. It can't give us different inputs when we invoke it at different times. But that's patently what getchar does. Like, if you call getchar twice, you can get like two different answers, right? And and yeah so such a function is not always going to return the same output. So so, so like so now you start getting questions of like, what is the meaning of our programs that we write, like um in the sense that the only way in which like we know how to prove things is through math. And it starts to appear that at least when you're reasoning about like programs in C or whatever, like math isn't working, right? Because things like getchar is not a real function. And so yeah, like how do you reason about this? um, so then, like, yeah, you can take a third example where once again I define a function called k, which takes two inputs and it returns a single output. And essentially it takes two arguments and it returns the first argument, completely ignoring the second. And right, and so like I can ask you what the output of this program is, and you will say the output is going to be like 10 and then 10, right? And so like at least in this case, it seems like we can reason about this program mathematically, right? Like we have a definition that says k of x y equals x, and wherever I see x comma y, I can replace it with x. But then, like, as usual, it's not so easy. Like I can create a function called error, which like instantly exits your program and then says I'm going to return a zero because it claims it returns an integer. um, yeah and Right, and then like I try to compute k of 10 comma error. Now like this program will never like even give you an answer, simply you know simply because like as soon as you try to evaluate it, error is going to get evaluated and the program's just going to quit. So once again, we can't use this reasoning principle that k of x y equals x, right? um, but like throughout math, like sort of the fundamental reasoning principle we have is that like if you define a function and you invoke a function with some arguments, then you can replace the invocation of the function with the body. But like this just stops working as soon as we get to like even like trivial programs such as this. Um, so and this kind of reasoning where we replace a left hand side with a right hand side, where you have an equality, like you have this equality, and so you'd like to replace this left hand side with this right hand side. That kind of reasoning is called equational reasoning, and this just doesn't work for C or C++ or Python or anything, because like the examples that I gave, they don't really use anything special about C or C++, right? You have exit in any language, you have getchar in any language. um, so now like this starts begging the question, okay, like is it even possible to reason about programs, right? Like I mean, yeah, is this even something that we can hope to achieve? Because it seems like these objects are like really ill behaved and they're not behaving like the math functions that we'd like them to behave as. um, so the answer is yes, and the longer answer is yes, it's complicated. And so on this slide I'm just going to like drop some like names, which we can discuss later, or you can go look up for the purposes of like learning things. But that's not going to be the focus of the talk. So like these are sort of mathematical tools that you can use to reason about C++. and it's complicated, and so yeah, like it's a hard thing to do. Um, so like there is an alternate route though. Like how do you escape from like all of these monstrously annoying problems? And the answer is fine. Let's just like clean slate. We're going to define a language where where like when we decide the semantics of the language, when we want to decide what happens, we're just going to design it such that what math tells us should happen, right? And it so now this language is by construction reasonable with, like, you can reason about this language using mathematics because we're defining the language in that way. And this language is of course like Haskell. So it's like as you keep learning Haskell, you'll keep feeling that it's really weird if you've learned any other programming language before. And the reason is that like Haskell chooses to take like some really strange decisions, which only makes sense if you look at it from this particular lens, where like if you sit down and think about it, and you ask yourself, okay, does this help me reason about a program mathematically? The answer is always going to be yes. Like the reason it does a weird thing is because doing the weird thing lets you reason about the program. Right, so that's sort of the preamble. Yeah, so now that we're done with the preamble, let's actually like get in and start playing with Haskell. Um, so I have an interpreter for Haskell here. So the Haskell interpreter is called GHCI. GHC stands for the Glasgow Haskell compiler, and GHCI is the Glasgow Haskell compiler interpreter. And like in this session, I'm mostly going to be using lists. So lists are a fundamental construct of the language, and I'm just going to be like showing lists. So let me split the screen here, so I can also have a Python REPL if I need it. Um, yeah, cool. So okay, like how do you create a list in Python? Well, you can say range 10, for example, and that gives you a range object. If you want to get a list from it, you'll say list range 10, and that gives you a list. So in Haskell, you'll say 0, 1, dot, dot, 10, and that gives you a list starting from 0, incrementing by 1, going up to 10. So if you say 0, 2, dot, dot, 10, you get the expected list of 0, 4, 6, 8, 10. Yeah, and like if your thing does not end on a boundary, it'll give you the, yeah, if you try to end on 9, it'll give you 0, 2, 4, 6, 8. Yeah, so like that's sort of the syntax of how you build lists using this dot dot notation. So it's like start second element from which it figures out the increment, and then the stopping element, like the final number. Um, yeah, right. But now in Haskell you can do something that's pretty interesting. You can say I'm going to define a list which starts with 0, increments by 1, and then just goes on forever, right? Um, so yeah, like what does this mean? Okay, so like the way you interact with lists in general is to use a function called take. So take takes two arguments. One is how many elements you want to take from a list, and the list itself. So in this case, we're saying take two arguments, take two elements out of this list. So that gives us the first two elements. So naturally, if you say take 0, it gives you nothing. If you say take 1, it gives you that. If you say take 2, it gives you that. If you say take 6, it gives you the whole list. If you say take 100, well, it still gives you the whole list because you don't have any more elements. Um, so we can try to use this to interact with the nats list that we have. I can say take 0 nats and it gives me an empty list. I can say take 1 nats and it gives me the first element. Take 2 nats, 2 elements. Take 100 nats, the first 100 natural numbers. Take 1000 nats, the first 1000 natural numbers. Yeah, I think you see where this is going. So I can also ask it what nats is, in which case it just like sits and attempts to crunch out every single natural number, which is going to take a reasonable amount of time. So I'm just going to kill it there. But yeah, but you can ask it what that is, and it'll happily like give you an answer, and it'll keep giving you larger and larger naturals. Um, right. So, but like this seems like a really bizarre feature, right? Like, why would you ever want a language that does this? This is called as lazy evaluation, by the way. Like the ability to build sort of infinite structures. Um, yeah. So the question is like, why would you ever want such a thing? And the answer, as with everything else in Haskell, is because this lets us reason about programs. Um, Yeah, so once again, let's try and do the kxy example. So the way in which you define a function in Haskell is you say let, and you then give the function name, and you then like tell it what the names of the arguments are, and you say that this is equal to what you want it to be. So in this case, I'm defining a function called k, which takes two numbers and returns a number. So k times 20 gives us 10. So like that's a pretty reasonable thing to do. Right, so we know what k is. Now we need an analog for like error or exiting or whatever. So the analog for that in Haskell is a thing called error, right? And so like here I ran error and it said call stack error, in this thing. And so like for example, I can ask it what 1 plus error is and it'll tell me, hey, that's an error. But now I can ask it what k10 error is and it'll say 10, right? So in a sense, just having this thing that produces an error does not instantly cause our program to fail, as it would in the C case, right? When I called k10 error in C, this just fails, because whereas in Haskell when I try this, it succeeds. So in Haskell, you can equationally reason about programs. And the reason that's possible is because of this lazy evaluation. So the way in which that works is essentially something like this. So let's say you try to evaluate k10 of error of erg, right? So the way in which it evaluates is something like this. So you're asking for the value of kxy. Now, what does kxy need to be evaluated? Well, it needs x, right? So then the Haskell compiler, it then goes and asks x, hey x, tell me your value. And x says, hey man, I'm 10. And so that returns the answer 10 to you. So y is like entirely ignored in this process, which is why it's in black. Like the compiler, the runtime literally doesn't even look at what this is. Like it could be anything for all you care. And the compiler is still going to like give you the answer 10. And this needs laziness, because the idea is that when you tell me error erg, I'm not going to compute this. I'm just going to keep a note that says, oh okay, when you want this value, I'm going to say error erg. But like as long as you don't ask me for this value, I'm not going to compute it, and things remain safe. So the reason why we get an error in addition is because like is let's say you try to add two numbers, then you need to know what the left hand side is and you need to know what the right hand side is. Like you can't compute the sum of two numbers without knowing both of these things. So when you as the user ask Haskell to add like 10 and an error, it's going to ask 10, hey dude, what's your value? And that's going to say 10. And then it's going to ask error, hey dude, what's your value? And it's going to like throw an error, right? Um, so that's sort of the reason why Haskell provides laziness. And the reason we want laziness is because laziness allows us to perform equational reasoning. So essentially, because Haskell is lazy, you can always replace the left hand side with the right hand side, and it's always safe to do so. And you can write a proof that it's always safe to do so in Haskell, but we're not going to do that now. Right. So now the other thing that sort of distinguishes Haskell from other languages is the existence of types, like C++. So C++ has types that you sprinkle everywhere. Python doesn't, and Haskell has like lots of types that you sprinkle everywhere and are powerful. So I'm going to like I'll try to explain what I mean by that. Um, so you can sort of ask the interpreter what the type of foo is, and that's a string. Like you write a string by putting it in double quotes, and it says foo is a list of characters. I can ask it what foo is, and it says foo is foo. Um, Similarly, you write a character by putting it in single quotes, just like you would in C++, and that just evaluates itself. Right. And so now, like, because a string is a list, I can once again use the functions that I had before that let me deal with lists. And and so like I can say take two characters out of the string of three characters, and you get the exact same behavior. If you try to take zero, it gives you the empty string, right? So like what is the type of take? So we can ask the interpreter what's the type of take, and the type it says is this. So it takes an integer and it then takes a list of any type a, and it then returns a list of the same type. So these are the inputs and these are the outputs. So like that's how you read a Haskell signature. So there is a function called take, whose signature is that it takes two inputs, one of type int and one of type list of a, and it returns an output of type list of a, right? So that's the type of take. And yeah, so what we should sort of read this a as saying it quantifies over all types. So we're saying for any choice of type called alpha, my function can take a list of that and it can return a list of that. So if you're familiar with templates, then in C++ this is something like writing a template type name t, right? So that's sort of the analog if you know what templates are, or template type name a in this case because a is the name of the type. Um, yeah. So now like let's try to do something illegal. Like let's try to take out of a character, which should not be possible because take says, hey look, I want a list. I can't like take out of a character. And it says, yeah, I couldn't do this. So it says it couldn't match expected type. Okay, let me call this Z. So it says it couldn't match expected type list of A with actual type character. And yeah, so if we look at the types, oh, god damn it. So if we look at the types, then this has type character, this has type list of a, and these two don't match. Yeah, and so therefore it throws an error, right? So that's how the type system works, and it's pretty reasonable. Now, okay, but like we defined this function called k, right? And I never wrote down any type where I actually defined it. I just said this. So, and now I'm telling you that everything has a type in this language. So like, what's going on? So okay, let's just ask it what the type of k is, and this is what it says. So here's how we read it. There's a function called k, which takes two arguments and returns one argument. If the first argument has type p1 and the second argument has type p2, then the answer has type p1, which is sensible because like in the function we're only returning the first input and we're completely ignoring the second output. So I can call like k1x, k1 list of 1 2 3, kx 1 2 3, like whatever your arguments can be of any type, and the return value is going to be the type of the first argument. And the interesting thing about this is that like I never told Haskell, um, yeah, so like I never told Haskell what the type of this should be. It just figured out the type. Yeah, so like this is called type inference, and some languages do this locally. So yeah, so like so if you've ever programmed in Rust or something, you can omit the types of, let's say, local variables or whatever in Rust. But then in Rust, whenever you define a function, you will need to give it a type. Whereas in Haskell, it can infer the type of anything. Like here, I defined a function whose type got inferred automatically. So this is called as type inference. And so like, so in some sense, you can write programs as if you were writing Python without caring about types at all. But then you know, in the background, the compiler is actually figuring out types, and it gives you an error if you like ever screw something up. So that's something that's really nice and that most other languages don't have. Um, and once again, okay, like why do they try to do this fancy type stuff? Well, it's because if you have a function from A to B, then like you can only evaluate it if the element of the input belongs to the input set, right? Like otherwise you'd have an error or something. So like and it's like to reason about functions, this is the only reasoning rule we have. So Haskell wants to reason about things mathematically, so it builds a system which tracks types so that we can reason about functions mathematically. So like that's sort of the reason why Haskell tracks types, because we need types to reason about math. Um, yeah. Right. So next I'm going to sort of get into some of the philosophical differences between like Haskell as a language or Haskell as a community and like most other languages that I know of or like I'm aware of. Yeah, so for example, right, we can take this Python program, um, which yeah, which which essentially tries to build a string a space b space c space d. So I can run this space dot join a b c d, and it gives me the string a space b space c space d, right? Yeah, like so far so good. But then like maybe I don't know Python and like I have no idea what that's supposed to do, so I go and like look up the standard library documentation. I don't go and like look up some arbitrary tutorial or Stack Overflow or something. I go like to the source of truth, right? And that here's what the document says. So it says string.join iterable. Return a string which is the concatenation of the strings in iterable. a type error will be raised if there are any non-string values in iterable, including bytes objects. The separator between elements is the string providing this method. Now, like this, so like this is sort of, yeah, this is indicative of like the exact same problems that we had before, right? It's like as soon as something throws an error, or like or yeah, like as soon as you call exit or something like that, we stop being able to reason about programs mathematically, and the fact that it raises a type error is going to screw us over. And like, yeah, and like even the definition of this has like exceptions, like it says if there are any non-string values in iterable and blah blah blah. So it's sort of a mess. Like it's a natural language description of something that we'd really like to have a more mathematical sense of. So yeah, like now the exact same function written in Haskell is to call a function called intercalate, which says intercalate this string between these strings, right? So I'm going to show it. Let's say import data.list, and let's say intercalate this between A, B, C, D, and it produces like the same answer. It says A, B, C, D. Um, but the way in which Haskell documents this is to just give a type, right? Like, which is the same thing to do. It says, yeah, so I'm going to take a string, and then you give me a list of strings, and then I'm going to produce as output a string. And the document says, intercalate x's x's is equivalent to this other thing, concat intersperse x's x's. So essentially, the way in which Haskell documents this is to give you an equation. It says intercalate x's is equal to concat blah 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 whatever. So it's like the very Haskell documentation talks about things mathematically. It says, look, the meaning of the thing on the left hand side is the meaning of the thing on the right hand side, and the only reason you can dare to do such a thing is because Haskell's been designed to let you reason about programs this way. So like yeah, because you have lazy evaluation and all of that, only then can you dare to even write such a thing in your documentation. um, yeah, and then it has a blurb about like informally what the thing does. It says, yeah, it says it inserts the list x's between the lists and x's and concatenates the result. Now, like, notice that in some sense it's talking about lists, it's not talking about strings, right? Like, whereas here we were talking about strings. Why is that? Well, so I sort of lied. The type of this is not the type of intercalate. In fact, the type of intercalate is something even more general. So notice that if you take a string and a list of strings and produce a string, but a string is just a list of characters. So that's equivalent to taking a list of characters and a list of characters and then producing a list of characters. But really, this function doesn't even care that you're trying to concatenate strings together. So you can just say, give me a list of anything and a list of anything, and I'm going to put the elements here in between the elements here. So, for example, this is a perfectly fine program to write. Like you can say intercalate the list 1 comma 2 into the list of lists 3 4 30 40, and in which case it's going to put this list in between these two lists, right? Like there is no reason for intercalate to restrict itself to strings or something. Like it's a super general function. um, so the Haskell library chooses to define it in the most general way possible. Why? Because that's the philosophy of Haskell, right? Like we want to reason about things mathematically in the most general way possible. Oh, and like I'm not making this up. This is the actual documentation on the website. So like if you want, you can go and check me up. I've copy pasted the yeah the blurb from the documentation. Um, right. So now like let's try to like sum over a list of numbers, right? Now, how would you do this? Well, there's a function called sum, and it lets you sum over numbers. So yeah, that gives you the expected answer. Once again, if we read the documentation, it says sum starts and the items of an iterable from left to right and returns the total. The iterable's items are normally numbers, and the start value is not allowed to be a string. Like I mean, once again, it's super annoying. Like there's some exception. It says are normally numbers. Okay, what about abnormally? What can they be? And like it's just a complete mess. And it keeps referring to this thing called iterable. Like what does that even mean? Um, yeah, whereas on the Haskell side, once again, you call a function called sum, and yeah, like you give it the list and it produces the answer. It says 10, so like, yeah, the function works. But like once again, what does the documentation say, right? Because we're trying to learn the language. So what does the documentation say? Um, Here's the documentation says. It says the sum function computes the sum of the numbers of a structure, right? And now the type signature is starting to get complicated. So there's this foldable t comma num a implies t a arrow a. So how do we read this? Okay, so first of all we can specialize this and we can think of it as a function from list of int to int. um, but here's how you read this. So it says if you have a structure t which is a foldable, meaning a foldable is a thing that you can sort of process in a given order, and you have a type called a which behaves like a number. And so then if you give me a ta, I'll give you an a. So an example of a t is the type list and a is int. So if you specialize it to that, then you get that list int arrow int. So yeah, the type is actually ta arrow a, but if you specialize and say t equals like list and a equals int, then the type becomes list int arrow int, right? And so like this type signature communicates exactly what the function does to anybody who knows Haskell, and the blurb describes in general what the function does. So sum like allows you to sum over anything that is a foldable. Now now like so so the difference that I see majorly between these two examples is that Python keeps using a term called iterable, and like if you try to go and read in the documentation what iterable is, you're not going to get a good answer. Whereas in the Haskell case, it says it is something called as a foldable, and like as we'll see, we're going to get a concrete answer for what a foldable is, right? So this notion of iterable or this notion of something you can iterate over is something that's left informal in Python, but is something that's formalized in Haskell. Um, yeah, and okay, like you can try to evaluate sum of all natural numbers, and it's not going to terminate. So, like I just wanted to show an example of a computation wherein, like you can go on computing forever in Haskell if you ask it to do something actually impossible. Um, but yeah, right. So we also had this other thing called num. So like we have two questions: what is num? What is foldable? Right? So okay, so this is the definition in Haskell. So it says class num a var. So like this is the syntax, and what this means is any type that you want called a is a number if certain conditions are satisfied. Now, intuitively, what do we think are numbers, right? We think integers are numbers, we think rational numbers are numbers, we think like real numbers are numbers, and so on. Um, so Haskell attempts to formalize this. So it says, okay, a thing is a number if you can implement these operations on it, called plus, called minus, called multiply, which take two arguments and return an argument, right? And because they're numbers, you might also want to be able to do things like negate them and take their absolute value. And you might also want to be able to ask about the sign of a number. Now, like this is another great example of the way in which Haskell's documentation differs from like most other languages. So the documentation says, well, the functions abs and signum should satisfy this mathematical law in that like this law should be satisfied, right? Which is something that you'd never see in any other language, and like I haven't seen in any other language except Haskell. So the community is obsessed. Like they always document things like this in terms of the mathematical basis for things. Oh yeah, and right, and then like within the documentation, they also ask to have associativity of addition, commutativity of addition, negate is the additive inverse, and like all of the other reasonable properties that you'd expect for multiplication and for distributivity and whatnot. So like all those. So in some sense, the Haskell documentation for what is a number like literally lists out the mathematical properties that you need out of a number, right? That's the documentation. And once again, the link is posted if you want to go check. Um, Now the next question is, okay, what's foldable? So a foldable is an object one can accumulate answers on. So in fact, I'm going to show an example of a thing that is a foldable that's not a list, and then we'll like go on to see what we can do with this. So for example, a set of things is also a foldable. So I can say import data.set, and then I can say let x equals data.set.from list 1 2 3, and this lets me build a list. This lets me build a set of three elements called 1 2 3, and then I can build another set of elements called 2 3 4, and that gives me another set, and I can take their union, Oh my god, okay. I can take the union and it says 1 2 3 4 because x is 1 2 3 and y was 2 3 4. Yeah, and I can call sum over x or sum over y, and Haskell lets me do this because it knows that a set is a collection of things which you can accumulate over, or like, yeah, or gather answers over, or you can iterate over a set. So like, this is type check, right? Like the compiler actually, yeah, checks my program for me. And if I screw up, it gives me an error. So like, once again, if you try to go look at what foldable is, yeah, like it gives you some definition where it says something is a foldable if whatever you have a monoid, things happen, blah blah blah, and it gives you laws to reason about what a foldable is. Like it says that this left hand side is equal to this right hand side and whatnot. Yeah, so like we're not going to get into this because getting into this will then get into what is a monoid and like all of that stuff. But I'm trying to get across the fact that like in Haskell, like you can start with the question of what is an iterator, and in Python you'll just get some description in English, whereas in Haskell you'll get a mathematical thing with rules that you're supposed to follow, and that's the definition of an iterator in Haskell, right? So like it's worthwhile to learn Haskell if you want to know what an iterator means in some sense. Like learning Haskell will tell you, and at some point you'll be like, oh yeah, that's just a foldable. So like this is sort of the general philosophical difference between Haskell and most other languages, right? Like it's the philosophical difference between that exists in math. Like why do we study linear algebra? Because it turns out that lots of things can be solved by linear algebra. So yeah, like that's a link of things that can be solved by linear algebra. And Haskell also attempts to study things at the right level of generality, or like using the right mathematical descriptions of things, like the foldable or monoid, or a thing called num, which describes all numbers, or a thing called list A, which describes all lists and not just talk about strings or whatever, right? Like string.join versus intercalate. Like one is clearly more general than the other, and like intercalate is arguably at the right level of generality for you to want to do this operation, right? There's nothing special about strings. And again, what's an iterable and foldable answers the question. Yeah, so like this is sort of to me like the main reason as to why someone should learn Haskell, because it sharpens your thinking about things that we use carelessly in other languages, which are very carefully defined in Haskell. Um, okay, so right, so now like let's sort of get into a couple of examples and like see writing Haskell programs in action, maybe, as sort of like a whirlwind tour of, yeah, like what writing stuff in Haskell is like. Um, yeah, so for example, let's say we want to implement Fibonacci, right? So what is Fibonacci? Well, it's a sequence. So let's say I write a function which takes n and produces the nth Fibonacci number, right? So here's the Haskell definition. You say, okay, the fib 0 is 0, fib 1 is 1, and fib n is fib n minus 1 plus fib n minus 2. So like this is the mathematical definition that you'd write. Whereas, so like if you were trying to write something, if you're trying to define the same thing in Python, you'd need to have a bunch of if statements, right? You'd say if and double equals 0, return 1, elif and double equals 1, return 1, else return fib n plus fib n minus 1, or whatever. Like you need to write those if statements. Um, Whereas in Haskell, like you just write that. Like you literally just write out that definition. And then if you were to like load the program, uh, and run it, yeah, it lets you run the program. So you can ask it what fib 0 is, it says 0, what fib 1 is, it says 1, what fib 3 is, what 4 is, what 5 is, etc. And it lets you ask for the nth Fibonacci number. Um, right? So like so far so good. But the difference is in some sense the way in which we wrote it. This is like much closer to the way in which like you'd write it mathematically. You'd just say, hey, this is what happens in this case, this is what happens in this case, and this is what happens in this case. Um, yeah, but now maybe we want to produce the list of all Fibonacci numbers, right? So how do we do that? Like, how do we write such a program? Um, right. Well, so the way in which we do that is by using a function called map. So so map is a function that takes as input a function and a list, and it then calls this function on every element of the list. So let me explain what I mean by that. Let's assume I have a list 0, 1, 2, 3, and I want to convert this list into a list of fib 0, fib 1, fib 2, fib 3, and that is the answer. But I could also write this as map fib 0, 1, 2, 3, and that also gives me the same answer, right? So map is a function that takes a list, it takes a function, takes another list, and applies this function to every element of the list. So yeah, that's what map does. Now using this, I can define all the Fibonacci numbers. Right? I can define the entire Fibonacci sequence. I can say fibs is map the nth fib thing onto onto the natural numbers, and this is something I can do, and I can take the first like 5 Fibonacci numbers or something, and it gives me the answer, or 6 Fibonacci numbers, and it gives me the answer. Um, yeah, so like this is sort of one of the nice things about laziness. Like often in mathematics we have these objects which are really infinite, and we would like to talk about them, and you simply can't. Whereas in Haskell you can just talk about infinite structures, and you can just like easily pull out how much ever you need from the infinite structure at any point in time. um, yeah, and also like this function map, it's an example of a higher order function, because what's called as a higher order function. So notice that this thing called map, it took a function itself as input, and yeah, so such a thing is like this sort of thing where you take a function as input and you use it to manipulate other objects is a really common thing that you do in Haskell. And so that's sort of why it's called functional programming, because you write functions that operate on other functions. um, yeah. And so if you now ask what's the type of map, well, okay, let's not do this now. We can do it later after the talk about what the type of map is. But yeah, you can think about it. Um, yeah, but then there's another way to write Fibonacci. So notice that Fibonacci in fact satisfies a recurrence. So the zeroth element of this list fibs is 0, the first element of this list fibs is 1, and the nth element of this list is the n minus 1th element plus the n minus 2th element. So that's just the syntax for taking the nth element by the bang. Yeah. Um, but then like we can also compute it this way. We can take fib 0, fib 1, fib 2, fib 3, and then we can like chop off the first element and take fib 1, fib 2, fib 3, fib 4, and then we can add these two up. Then we get fib 0 plus fib 1 is fib 2, fib 1 is plus fib 2 is fib 3, fib 2 plus fib 3 is fib 4, and so on. So like this is another way to compute this list called fibs. So yeah, so the way in which we can do this is we can say, okay, I start with a list. I start with the element 0. I then append onto that the element 1. So the symbol colon is used to append elements to a list. So if you have the list 1, 2, 3, um, I can say 10 colon L, and that gives me a list with 10 as the first element of a list. And you can build lists this way by simply adding elements to each other. So this is the empty list. This is one added to the empty list. This is one followed by two followed by the empty list, and so on. Right. So that's how you build a list in Haskell. So we're trying to build this infinite list called fibs directly without having to write this auxiliary function called fib. Um, so okay, we know the first element is 0, the next element is 1, and then everything else is defined by some recurrence that we have, which I'm going to call fibrec. And so what should fibrec do? Well, so fibrec should take the original list of fibs, it should chop off the first element, and then it should add the two up, right? So let's take it slowly. So we have a list, let's say 0, 1, 2, and we want to chop the first element off. That's tail, that chops the first element off, and then once we chop them off, we now want to add these two lists together. But this is like a recursive call wherein fibs refers to fibs refers to fibrec, and fibrec refers to fibs. Yeah, and right, and we can define this function that adds elements together, and we're calling it zip add. So essentially the idea is, yeah, So let's see. Yeah, take one. No. Yeah. So the idea of this definition is like this. We're defining a function called zip add, which takes two lists as input. So the first list has x as its first element, and the rest of the list is x's. The second list has y as its first element, and the rest of the list is y's. And what happens, and the output list has x plus y as its first element, and recursively we ask it to add the other elements together. So you can imagine it as if you're zipping the two things together with this plus. So the plus operation is like a zip which you're pulling. So we've added the first two elements, we've added the next two, we've added the next two, and then we want to add all of them together. So that's sort of what the program is doing. Don't worry if it doesn't make sense. Like I just want to give you a rough idea of how you can do this. This is not really meant to be sensible. This is just meant to give you a sense of how you can use laziness. Yeah, so right, so essentially we write this definition, but then you can like massage the definition a little bit, and you can write it as something like this. So you can say that the Fibonacci sequence is 0 followed by 1, followed by us adding the elements of Fibonacci one by one to the rest of the elements of Fibonacci one by one after chopping the first element off. So like this is the definition you can write. So I will load the file into Haskell 52. Yeah, so if I load this function, mm, 52, then yeah, I can ask it what the first five elements of fib is, and it will tell me the answer. And the idea is essentially we're defining the list of Fibonacci numbers to be 0 followed by 1 followed by the elements of the Fibonacci sequence added with the rest of the elements of the Fibonacci sequence one by one, which is literally what the recurrence of Fibonacci asks us. It says start with a 0, then a 1, then for any other element just add the previous things together, right, like as we did here. So this sort of allows us to um, yeah, so this is only possible because we're using laziness. We're both defining the object called fibs and recursively using the object called fibs to produce more elements of the thing while we're building it. And this sort of definition is only possible because you have laziness. Yeah, like this takes a while to get used to and like understand. But in some sense, to me, this is how I think of Fibonacci now. Like the Fibonacci sequence is literally this for me. And yeah, if you learn Haskell, you too can think about Fibonacci sequences. Yeah, so like, so I guess for me, like, yeah, so like at least for me, this is sort of like the reason why I would encourage people to sort of like learn Haskell, because I don't know if it's going to help you get a job. I don't. It's unlikely. I don't know if it'll help you get better at CP. You should ask Anirudh about that because he's planning to stream doing computer programming in Haskell. I don't know if it'll help you get a GSOC project. You might, because the Haskell community is small and they always accept like people who are interested in doing things. But in general, I feel that like learning Haskell lets you learn a bunch of math, and it lets you learn what computation is and like how best to think about things. Like what is iteration, what is an iterable, it's a foldable, what is the Fibonacci sequence, it's that cute one-liner definition that I showed you, which probably makes no sense to you but will if you learn Haskell, right? um, yeah, so like Haskell was sort of designed to help people understand what computation is and like how to think about computation. And in fact the Haskell motto is like avoid success at all costs, in that they didn't want to become a successful programming language. They wanted to be a sort of safe space where people could play around with ideas and people could like try crazy things without needing to like worry about the real world. Like Haskell is not a really fast programming language. It runs really slowly. Doing all this lazy programming has making it lazy has quite a lot of impact on runtime, but they don't care because for them the goal of Haskell is to create a language that that helps you reason about programs, that helps you think about math cleanly. um, so that's sort of the Haskell motto. But like this is a good example of where a comma really matters, because some others claim the motto is avoid success comma at all costs, meaning we still want to succeed but not if success means that Yeah, not if success means that we need to do something crazy, or like violate mathematical beauty. Um, yeah, so that's sort of the purpose of Haskell as a language, right? So yeah, like what is Haskell? Haskell is a programming language which is lazy, which is strongly typed, like in that everything has a type, and it is pure. We didn't really discuss the pure part, but essentially, yeah. And so the Haskell programming language to me is more than the language; it's the community, which is crazy about always having the right abstractions and defining things the best way, and sort of like getting to the heart of what something is. Yeah, so that to me is what Haskell is, and like that's what I've learned from learning Haskell. Like, I think I became a better programmer simply because I learned how to think cleanly about like lots of things, and I wound up learning a lot of math simply because of learning the language, because the entire language is defined like this. um, and yeah, I've put up some references on where to learn. I'll put up the slides, so yeah, you can get access to all the links and whatnot. So yeah, thanks. I guess that's the end of the talk.
Yeah, so all right, if anyone has any questions, they can ask.
Yeah, the image you drew for Zip was really nice. I did not know why it was named Zip till today.
Okay. Yeah,
Yeah,
it's
I mean
because yeah,
it also
yeah,
nicely captures the laziness. Like as you pull the zipper, it requires the next value.
yeah, exactly.
So yeah, you don't
Uh,
need the entire thing.
yeah. So like there's a diagram here. So like yeah, as if you want to compute 2, you need 1 plus 1, so that gets computed. Next to compute 3, you need these two, that gets computed, and so on. So this is the laziness of the computation essentially. um, yeah. Yeah, I'm glad you liked it.
So if no one has any questions,
Uh,
we can.
yeah, I have one.
Yeah.
Oh,
So, if what's the difference between Haskell and other functional programming languages? Like, uh, where do they differ? If everything is so mathematically defined, how do they
Yeah.
differ?
So yeah, so I would say that Haskell is probably the purest, like in the sense that Haskell is the only functional language that's lazy for a start. Like all of the others, like OCaml or whatever, they're all strict. So Haskell is one of the only languages that's lazy. And then I also mentioned this thing about being pure. So like I didn't really get a chance to go into it, and like maybe it's too much. But the general idea is that like in Haskell, it separates sort of like actual values and things that are not values. So for example, if you think about what, like in C, getchar claims it returns an integer, whereas in Haskell, getchar says no, like I'm not going to give you a character, I'm going to give you a thing that's called as an IO character. So it sort of separates, um, yeah, so it sort of separates the things that we cannot reason about well, like things like IO or whatever, which aren't mathematical, using this thing called IO. And then it like builds a mathematical framework to let you reason about these things. So like whatever, if you Google for Haskell, the thing that you'll maybe see at some point is a thing called as a monad. What is a monad? I'm not going to like cover it here, but essentially it's a thing that lets you take those programs that I showed before, like in C. If you were to rewrite them in Haskell, you could reason about them mathematically, because the way in which you'd write those programs involves these things called as monads, and that lets you reason about them. So that's why people say Haskell is a pure, lazy functional programming language. And so the pure part has to do with, so the pure part is one thing that makes it different from other functional languages, and lazy is the other part that makes it different. So yeah, it's the combination of these two things that sets it apart.
Thanks.
Yep, you're welcome.
so yeah, I think we'll end it at that. So I'll stop the recording.
Cool.